The second way that, that crosslinks can form in gels doesn't involve proteins folding and unfolding, but this involves situations where there aren't proteins around, that the gels are made out of the polymers are made out of carbohydrates, and we need ways for the carbohydrates to stick to each other. And this occurs through the use of a binding agent. So the most important example of this phenomenon that we will discuss this week is spherification. This is the beautiful creation of Ferran Adria, in which a small shell of gel is created around a very, very delicious food. And I now want to describe to you how that actually works. That is, what are the elements of that? And to do that, let's just start with a recipe. So here's a recipe for spherification. And this is a recipe for something that Ferran calls spherical tea ravioli. It basically contains some sort of a tea mixture, and he then inside, and then he forms a gel around the outside. And we'll talk about the physics of how the outside of the gel is formed in a little bit. But first, let's just focus on what the ingredients are. So if you look at this ingredient list, you will notice that there are two ingredients which seem a little bit unusual. One is called sodium alginate, and that actually is in the interior of the tea. And the second is called calcium chloride, which is essentially a type of salt. So sodium alginate is a polymer that basically comes from seaweed. It's a carbohydrate, and that, it turns out, is the molecule that actually is the essence of the gel in this material. So alginate consists of polymers, and it turns out that those polymers, when they are in solution, are negatively charged. So they have an electrical charge and they're negative. And as you all know, electrical charges that are negative repel each other. That is, they won't stick to each other at all because negative charges don't like each other. So the question that we have to ask ourselves is, can we make them stick? So the first clever idea that you might have to make them stick is that, well, maybe we should add positive charges. And so then you would think to yourself, well, where can I find positive charges in cooking? And certainly a good source of positive charges is table salt. So table salt is made out of sodium chloride. If you pour it in solution, the sodium atom and the chlorine atom will dissociate, and you'll have positive charged sodium atoms and negative charged chlorine atoms. The negative charged chlorine atoms, of course, won't like the alginate either, but the positive charges are going to stick to it and neutralize the negative charge. Now, so now if you imagine it, we have this polymer, and on the polymer we have these negative charges, and now there are these little positive charges that are sticking to it, and that's all great. So now the polymers don't like each other as much. They like each other more than they did before because they're not as negatively charged, but they still don't stick to each other, so it didn't work. So it turns out, though, that if we use a different type of salt, instead of using sodium salt, we use calcium salt, then we can solve this problem and make it work. And that is because calcium salt, the calcium ion, actually has two positive charges. It's doubly charged. So when the calcium ion sticks to the alginate molecule, one of the positive charges will cancel out the negative charge, but there's still a positive charge left. And that positive charge can then stick to another alginate molecule, thus allowing the two molecules to stick to each other. So if you remember back to the little demonstration that we described that you should all go home and do with your friends, where you hold hands with one friend and another friend, this is the same sort of thing. The calcium ion is essentially something that can hold hands with two friends, and if the calcium ion holds hands with two different friends, it will bind those friends to each other, and if the number of such crosslinks becomes high enough, you then create a gel. So in a little bit more chemical detail, so this is a sort of simple, but really, I think, quite accurate view of what's going on when you add calcium salt to alginate. This is a more chemically detailed version of what's going on. You see the alginate molecule has a chemical structure, and there are places within it that the calcium molecule can bind, thus causing two alginate polymers to stick to each other. It turns out if you look through recipes involving what chefs call hydrocolloids, there are many different types of hydrocolloids. So alginate is the first one that we've seen, at least this week, that is a bit different than the types of materials we usually cook with, at least I usually cook with. But in fact, there's a whole list of different hydrocolloids that can be used. Another example is a molecule called gelin. There's guar gum, there's xanthan gum. There's a whole list of hydrocolloids, and these hydrocolloids can all be used to make gels, and they all have slightly different properties depending on what you're trying to make. And I just like to highlight the properties of a couple of the other ones, just so that when you start to look at recipes, as we hope you are, that that the chefs in this course are creating, you can try to distinguish what must be going on. So one recipe that is really quite elegant is Heston Blumenthal's recipe for what he calls hot and cold tea. So in this recipe, what he does is he takes a cup of tea, and he then draws a vertical line through the cup of tea, and on this side of the tea, he basically creates, he has at one temperature, and on this side of the tea, he makes it at another temperature, and it is designed so that when you drink it, your tongue, half of your tongue feels the hot temperature, and the other half of your tongue feels the cold temperature. I've never tasted it myself, but it must be a very interesting sensation. So if you think about how you would do that, what you need to do is you need to make both sides a gel. They have to be solids because otherwise they will be weak, they will mix with each other. But they have to be solids which have the same elasticity at different temperatures. And it turns out that the way that Heston Blumenthal was able to do that was by using a material called gelin. And that is a material that basically, it's a carbohydrate, in the same way that alginate is. But if one goes and looks at how the crosslinks are made in gelin, this is a subject of active research. Here, for example, is an abstract of an article, a review article that was recently published on the gelation of gelin. And when you look at it carefully, what it shows is that the mechanism for cross-linking gelin is actually much more like an egg. That is, it's much more having to do with structural change, protein unfolding, that sort of thing, than it is like the alginate example where charge are leading to cross-links. So gelatin is really quite similar. If you look into the chemical details of gelatin and how the cross-links form there, I mean, of course, when you make Jell-O, you have to first heat up the gelatin. That is a red flag that you must be unfolding something, and then then cross-links form. And so that's actually much more like an egg than spherification. So the reason that there are so many different types of gels is that, of course, one would like to be able to manipulate the formation of gels and cross-linking in lots of different ways. So another of my favorite examples, just to give you one more example of this, is methyl cellulose. So one of Ferron's other creations was hot ice cream. So the question here was, how could you make something which had the same texture of ice cream but actually was a solid at a much higher temperature, like 50 or 60 degrees Celsius? And what Ferron was able to show was that, in fact, if you use methyl cellulose, which is a gel that has a much higher melting temperature than gelatin and other